All right, this is Mr. Kingsbury from Algebra 2. We're studying rational equations, and today I want to talk to you about writing equations. In fact, our essential question is, how do I write rational equations given a situation? We're going to look at three different types of situations. We're just going to write them. So here are the three different types. We're going to have distance, rate, and time. We're going to have work problems, and we're going to have unit price problems. And in fact, they each have kind of their own formula that we follow, and we'll use those to, I guess, set up different situations and so forth. Let me start at the bottom with unit price and work from there. So for unit price, the formula is, well, it's pretty generic. Unit price is like this: y equals some constant. All right, so you've got your cost per unit, right? We'll call that C, cost per unit, times number of units, which we'll call X, plus some non-changing fee or cost or something. I'm trying to think of what it, like a one-time fee kind of deal. And then we'll divide that all over, again, the number of items that you're buying. Now, a lot of times, problems like this have to do with splitting the cost of something amongst a lot of people. For example, let's say that we have AT&T. This is a great example. And I don't have the word problem to show you, but I will speak it out loud for you right here, okay? So AT&T is running a special where unlimited text and data are $50 plus $20 per line. So example one, we'll say $50 plus $20 per line. That's the So then the problem goes on and says, for example, if you had one line, you'd pay the $50 fee for unlimited data and then $20 for the line for a total of $70. The question is, what is an equation that could be used to determine how much you would pay for X lines? So it would look something like this. First of all, you have $20 per line. There are X lines. So 20 times X, that gives you the cost of X lines. Then we have to add that one-time fee in there, that flat rate, if you will. This gives us the total. We're going to take that total and divide it amongst all of the lines, and that will give us our cost per unit, which is, in this case, Y. For example, let's say you and 5 of your closest friends are going to split the cost of this cell phone, that the cost times $20 a line, plus to give you a total of $150. No, $170. Then you would divide that 6 ways, and each of you would pay that amount. Obviously, the more people that are in there, the less each one has to pay. That's kind of how it works. But for our purposes, this is how you would set that up. Not a big deal. How about another one? Example 2 here. How about a tour company? So they charge a flat rate of $50 for their tours plus $35 per person. So how much would it cost for X people to go on a tour? Well, $35 times X people gives the cost, the total cost for however many people, plus that $50 flat rate, and then you divide it amongst X people. So you get something like a total of $50 for the whole 150 plus another 100. Everyone pays like $35.50 or something per person. So that's unit price, and that's pretty straightforward. The next one would be work. This is the kind of problem where you're given some rates. You say so and so can do some kind of job in a certain amount of time. This other person can do the same job in a different amount of time. How long will it take them to do the job together? And the general formula looks like this. You have your time together, and you divide that by the first person's time alone. So we'll call it time alone number 1 for the first person. And then you do the same thing. You add those. Let me just do a couple. For example, let's say that Trayvon and Lauren are painting the living room. Now, Trayvon can paint the room in 3 hours. Lauren can paint the room in 5 hours. We're going to write an equation that could be used to figure out how long it would take them to do that together. Now, the first thing I want to point out is this. Trayvon can do it in 3 hours by himself. Lauren can do it in 5 hours by herself. That means together, they better be able to do it faster than the 3 hours or the 5 hours. If Trayvon can do it in 3 hours by himself, then with the help of Lauren, he should be able to do it a lot faster. So whatever our answer is, if we were to work it out, it would need to be less than that. And it just occurred to me that what I just said doesn't matter because I'm not making you solve it. So awesome. We don't know how long it will take them to do this thing together. So X is going to go on the top of both of these. We know Trayvon is 3 hours and Lauren is 5 hours. That's my equation. Pretty straightforward. Not much to it. And like I said, you don't have to solve it. So not a big deal. Let's see. Let me see if I can find another one here. So how about this one? Raquel and Anika are packing gift bags for a party they're hosting. Raquel can pack the bags by herself in 50 minutes. Together, they can both pack the bags in 25 minutes. How long would it take Anika to pack the bags by herself? So I like this one. No matter what the problem is, when it's a work problem, it's going to be some fraction plus some fraction equals 1. And you put the time together on top, and then the separate times on the bottom. So this says together they can do this in 25 minutes. Well, that's what's going to go on the top. One of them, Raquel, can pack the bags in 50 minutes like that. So that'll go on the bottom of one of the fractions. We don't know how long it takes the other person, Anika, to do that. So we're going to put an X there. So in my mind, it goes pretty much like this. Like together is on top and then separate and separate on the bottom. And it always equals 1. And remember, you're not solving it, so you don't have to worry about how do I solve this or coming up with a common denominator or anything like that. I saved the best for last, and this is the last type, and that is distance, rate, and time, because there are a couple different ways that we can set stuff up. Distance, rate, and time have an interesting relationship, and they form an equation, which you've seen before, especially if you've taken physics. You've seen this equation before. Distance, rate, and time. They have this equation. Distance equals rate divided by time. Here's the thing, though. We don't always use it that way. Sometimes we rearrange it so that rate equals distance times time. And sometimes we rearrange it, this will be very interesting, so that time equals distance over rate. So depending on what we're given and what we're being asked to find, we could use any one of these three. So it's really going to depend on the situation. Sometimes you have a situation where you're looking at how fast something or someone traveled going 2 different directions. And in that case, you're going to have 2 fractions that are equal to each other, and we can set that up. So let me see if I can give you one. For example, let's say that we have Julia and Gabby. They're on a riverboat tour on their vacation. So the maximum speed of the boat in still water is 10 miles per hour. The boat travels 27 miles downstream in the same amount of time it takes the boat to travel 12 miles upstream. We're going to write the equation to solve for the rate of the current. So here's what we know. We know that it is 27 miles downstream and 12 miles upstream. Those take the same amount of time. And in fact, I just said the most important part of that. You would think the numbers would be the most important part, but they're not. The most important part is where it says the same amount of time. So I'm going to use this one. I know, this is my example, that the time going upstream, we'll call it T sub U, is the same as the time going downstream. Now we know time is equal to distance over rate. That means the distance going upstream divided by the rate going upstream should equal the distance going downstream over the rate going downstream. And I realize there's a lot of little subletters there, subscripts. Don't worry, it's okay. So here's the deal. We know the upstream is 12 miles. So we're going to set up two equations here. We'll have our upstream equation and our downstream equation. So upstream will be on the left, downstream will be on the right. It says the boat travels 27 miles downstream in the same amount of time it takes to go 12 miles upstream. Actually, it says against the current, which will become important in a second. So 12 miles upstream, 27 miles downstream. It also tells us that the maximum speed of the boat in still water is 10 miles per hour. Now, I know you want to say that that's the rate, and that's certainly the starting rate. They both start at 10. Here's the problem. Going downstream, the current is pushing the boat faster. It may start at 10 miles an hour, but when you're going downstream, the current is pushing you faster. So we need to add in the speed of the current, which we'll call C. Going upstream, the current is pushing against the boat. So the 10 miles an hour it's chugging upstream is being slowed down because the current is pushing against it. So the rate is going to be whatever 10 is minus the strength of that current. And that works out really well because the question asks us to write an equation that could be used to find the rate of the current, which would be C. So we would set up something like this. So that's a situation where you're moving the same amount of time in two different directions. So you set up an equation equal to an equation. Sometimes, though, you will be given a situation where instead of being told, yeah, it's the same amount of time to go these two different distances because something is affecting it. And by the way, a lot of times these have a current or an air current or a wind current in it. The other time is when you're talking about the whole journey someone's making. For example, Casey runs a 15-mile race in 2 hours. For the first 8 miles, she ran at some unknown speed. For the rest of the race, she decreased her speed by 2 miles an hour. Write an equation to determine how fast she ran during the first part of her run. So in this case, we have a total time. So we know that the time for the first part plus the time for the second part is going to equal the total time. So we're going to go back to time equals distance over rate again. So we're going to have the distance for the first part over the rate for the first part plus the distance for the second part over the rate for the second part will equal the total time, which in this case is 2 hours. Now we know the total distance. The total distance is 15 miles. And it says for the first 8 miles, she ran at a certain speed. So we know the first one of the distance, let's call it the first distance, is 8 miles, and she ran at some speed, which we'll just call R. I don't like to use S because it looks like a 5. However far she ran at whatever the speed was for the second part, we know that that was some other amount of time, and when we add them, we're still getting 2 hours total. Now, since we also know the total distance was 15 miles, we can say 15 minus 8 is 7. So the remaining distance is 7 miles. So basically, they have broken this run she went on into two different parts. The first 8 miles and the remaining 7 miles. Now, they told us she goes some unknown rate for the first 8 miles. And then for the remaining time, or distance, I should say, she decreased her speed by 2 miles an hour. So she took this rate and decreased it by 2. So for the first 8 miles, she ran this fast. For the remaining 7 miles, she ran 2 miles per hour slower. So this is going to be my equation there that I could use to solve for how fast she ran during the first part. Fortunately, you're not going to be asked to solve. You just need to write the equation, which is great. But you should probably get used to something like that. Let me give you another one just just to be on the safe side, this will be our final example for the day. I'm not going to write quite as much down here. Fiona walked to a convenience store that was 2 miles away. Her walking rate on the way back was 0.75 of her walking rate on the way to the store because she's carrying a bag of snacks. And it took her 1 hour to make the round trip. So we're going to write an equation. In this case, we aren't told that the time going and the time coming back are the same. We're told that the two times add up to a total time of, in this case, 1 hour. Well, we're going to write an equation that could be used to find the rate that she walked there. It also says the convenience store is 2 miles away. So going there, she walked 2 miles. Well, she walked 2 miles. She walked a certain rate, which we'll call R, there. Coming home, she walked 0.75 of that rate. 75% of that rate, however you want to say it. So the coming back would be 0.75 R, and that would be our equation. She walked 2 miles there, 2 miles back. It's a total of 1 hour. Her rate there we'll just call R. Coming back, she was slower because it was 0.75 of her rate. And that is writing equations, guys. We'll do more practice in class. I have what do you call that? An activity we'll do out in the hall. But I think, pardon me for yawning, that you will get the hang of this really, really quick. This is usually one of the easiest parts of this unit. See you in class.